Have you ever really thought about soap? Just that simple bar you use every day. We're doing a deep dive today into how it's actually made, the chemistry behind it all. We'll look at small batches like in a lab versus massive industrial production. And there are some really surprising facts about soap itself and its a main byproduct, glycerol. We've got some detailed notes covering the chemistry, the procedures. It should be interesting.
It really is. And it all boils down to one core reaction. Saponification.
Saponification.
Exactly. Think of it as a specific acid-base reaction. You take an oil or fat that's your triglyceride, sort of the acid component, and react it with a strong base, a lye, usually sodium hydroxide if you want hard soap, or potassium hydroxide for liquid soap.
Okay.
And this reaction basically splits the fat, creating soap, which is technically a salt and glycerol. The hydroxide ion, the OH, that's the key player here.
That chemistry sounds neat, but making it work.
Yeah.
Going from, a small beaker to turning out tons for everyone, how does that leap happen?
Well, even in the lab, it's pretty involved. Safety first, always lye, is nasty stuff, corrosive, and it heats up a lot when you mix it with water.
Right, exothermic.
Precisely.
Yeah.
So you heat your oils, maybe sunflower, maybe soybean oil, to about 50 degrees C. You make your lye solutions separately. Then, critically, you combine them only when both are cooler, around 35 to 40 degrees. Stir until it thickens up. That's the saponification happening.
And then you just pour it out.
And pour it into molds, yeah. Let it set for a day or two. But then comes the really important part, curing. It needs to sit on something like parchment paper for about 4 weeks.
4 weeks?
Yeah, it lets the reaction fully complete and excess water evaporate. Makes the soap milder, harder. Then you wrap it, maybe in wax paper. That's because the glycerol left in handmade soap is a humectant. It grabs moisture from the air. Wrapping stops it getting sticky.
Okay, that's quite a process for just one batch. So for the mountains of soap, how do factories manage that efficiently? Must be different.
Oh, completely different scale, different techniques. Industry mostly uses two big methods. There's the batch process. Yeah. Kind of the older way. They extract oils, say, from crushed and steamed soybeans, mix them with sodium hydroxide solution in a big sealed tank, heat it under pressure. Then they add concentrated brine salt water and cool it. The soap solidifies and separates out.
Okay, fast process. And the other?
The continuous process. This is much more common now, way more efficient. It's all about precise, continuous flow. You feed a very specific mix of fat or oil and lye into a reactor. It reacts, then it's cooled just enough to what's called the graining temperature.
Graining temperature.
Yeah, it causes the soap to form tiny grains. And crucially, at that point, the soap is less dense than the surrounding liquid, the lye and glycerol mix, so it floats.
Ah, clever. Makes separation easier.
Exactly. It separates statically. Then the soap is washed, usually in a column, centrifuged to spin out the glycerol,
Yeah.
and any leftover lye is neutralized, maybe with a bit of coconut oil. This continuous method is really what made soap so cheap and available everywhere. It fundamentally changed hygiene globally.
That's incredible engineering. And all this chemistry affects the soap we use too, right? Like why some soaps feel different or work better.
Absolutely. You get hard soaps, usually sodium-based, tougher, good for laundry maybe. Soft soaps, often potassium-based, lather up more easily. Think toilet soap, shaving cream.
And what about how well it cleans? Does that change?
Oh, definitely. And that often comes down to your water.
Yeah.
Ever notice soap not lathering well?
Yeah, sometimes. Well, like on holiday, somewhere new.
That's probably hard water. It's full of magnesium and calcium ions. These ions react with the soap molecules and form this insoluble gunk. Soap scum. It basically stops the soap doing its job.
Ugh, soap scum, right.
Soft water doesn't have those ions, or very few, so the soap works much, much better.
So how does it work when it's working properly?
It forms these amazing little structures in water called micelles. Picture tiny spheres. The soap molecules have a water-loving end, polar, and an oil-loving end, nonpolar. In water, they arrange themselves with the oil-loving tails pointing inwards and the water-loving heads pointing outwards.
Okay.
So the oily, greasy dirt gets trapped inside the micelle, and the water-loving outside lets the whole thing get washed away by the water. Pretty neat mechanism.
That is neat. So it literally traps the grease. Okay, but soap isn't just about cleaning, is it? We mentioned the byproduct. Glycerol.
Right. Glycerol or glycerin. It's not just waste. It's incredibly valuable. It gets purified and sold. Honestly, its value helps keep soap affordable.
What's it used for?
Oh, loads of things. It's in paints. Cosmetics are a huge one. Some pharmaceuticals. It's used to make explosives like nitroglycerin.
Wow.
And
Yeah,
even in processing tobacco to keep it moist. Super versatile stuff.
that's a serious range. And the soap itself has some odd uses too, doesn't it? Beyond washing hands.
Yeah, a few surprising ones. You can mix soap flakes with water and spray it on plants to deal with aphids and other pests.
Really?
Yep. Or if you think you have a gas leak, like on a pipe joint, rub some wet soap over it. If it bubbles, you've got a leak.
Handy tip.
It can even act as like a temporary plug for a small oil leak in a pinch.
Yeah.
And some people swear by rubbing soap on insect bite to stop the itching.
Never heard that one. Okay, so we've gone from basic chemistry
Saponification.
through lab benches and huge factories
Continuous processing.
to water hardness, micelles, and even bug bites and explosives. It's quite the journey for something so well every day.
It really is. Makes you think, doesn't it?
Yeah.
And considering that fundamental chemistry and all these uses, it does raise a question. How might we innovate further? Could new tweaks in making soap or using it or glycerol impact things like, I don't know, health, new industrial processes, or maybe even environmental solutions?
That's a great thought to leave people with. So next time you reach for that soap, maybe give a little nod to the science packed inside. It's more than meets the eye.